What's up, sports fans? Hey there, Coach Spots here again. Shout out, this is to my Algebra 1 class. This is Thursday's lesson this week, dealing with solving systems of linear equations. Specifically, we're going to use the elimination method. All right. So if you notice the difference in today's setup versus what we did on Tuesday, is that now our linear equations are in standard form. Notice it's a column of x and a column of y equals our constant. Same thing down here. Now the elimination method only works when our terms are in columns. So notice I have my terms of x, my other like terms of y equals my constants. Okay, so this is typically how it's set up, where it's in this standard form, okay? And so the process is basically, if you have equal sides of an equation, they can be combined through addition or subtraction with other equal sides of an equation. That's basically the idea, is I can say this plus or minus this is the same thing as this plus or minus that. So basically what we're saying is we can combine equations additively and subtractively, okay? I don't think subtractively is a word, but additively, and thus the inverse of that would be via subtraction, okay? So if you notice, if I were just to combine the equations as they are, something magical happens here with my terms of y. Okay, first off, if I combine the equations by addition, I can take 3x and add it to 2x to make 5x, all right? If I also combine my y terms via addition, I have a positive y and a negative y, which completely cancels out. That's the whole goal of this, because right now we have two equations, and it's tough to solve two equations when there are two variables that we don't know. This is called having two equations with two unknowns. There's two variables that we don't know what the value is for each of them. But you all know how to create one variable equation. Sorry, you all know how to solve a one variable equation. We've done that so far this unit. So that's our goal right now, is to get to a point where we're solving a two variable equation when there's two of them by reducing it down to one variable. So if you look at this, by eliminating the y, and then don't forget we still have to combine this side, by eliminating the y, we get a one variable equation that we can now solve the old-fashioned way, right? Divide by 5, and we get that x equals 1. Let's save this for later. This is not the solution to my system. If you recall, a solution to a system is the point of intersection, right? It's a point that solves both lines. It's a point that lies on both lines, right? We've got two linear equations here. For all intents and purposes, basically what we're saying is we've got one line, we've got another line. Where they intersect, you have a point that happens to reside on both lines. This shared point of intersection solves both equations and therefore solves the system. So this is just the x value. We want to still find the y value. Okay, so let me clear off a little bit more space now that I've solved for x. So that's kind of step number one, is eliminate a variable and solve for the other one. And now it doesn't matter which equation we're going to choose. We're just going to plug in what we know x to be and solve it out. So I've got 2 times we know x is 1, subtracting y equals 0. Okay, so basically 2 minus y equals 0. I'm going to move the y to the other side. That makes this the easiest to solve. I move the y to the other side, it becomes positive y equals 2. And now we have our coordinate for our point of intersection, 1, 2. And that is the solution to this system. And we should be able to plug this point into the other equation to create a true statement. For example, 3 times x is 1, right, plus y, which is 2, should equal 5. 3 plus 2 does equal 5. Good. This point works since this point solves both equations. All right? Let's practice that now. So if you notice, this problem was a nice, straightforward, easy problem because our y's had the same coefficient but opposite, right? Equal but opposite coefficients, +1 and -1. -1 and +1 are equal but opposite coefficients, which canceled out immediately. That's our whole goal, is to eliminate one variable, okay? It's to cancel out a variable. If you look at our setup here, we've got x's, y's equals constants. I want you to identify which of our variables now has equal but opposite coefficients. Take a look. One of our variables has equal but opposites coefficients. Hold on one second. If you look at this, you should see that x has equal but opposite coefficients. When we have equal but opposite coefficients, we can just combine them through addition right away. Because -2x and +2x cross off, y plus 3y makes 4y, 1 plus 3 makes 4. We now have a one variable equation that we can solve. I divide by 4. I have a side note that y now equals 1. That's just a side note. That's not the answer. But that is half of our answer, is identifying the y value. Now we take that information that y equals 1 and we substitute it into either equation. I'm just going to plug it into this equation right here, okay? Since it's just right there for me. And I've got 2x plus 3 times 1 equals 3. So 2x plus 3 equals 3. Subtract 3 from each side. I've got 2x equals 0. Divide by 2, x equals 0. And that's allowed. We're allowed to have the value be 0. And so our coordinate is 0, 1. Let's plug that into the other side. Let's double check it. Plug in 0, plug in 1. So 0 plus 1 does equal 1. Good. Very straightforward. Okay? Next problem. Okay? Do we have any equal but opposite coefficients here? No, we don't. We have equal coefficients, but not opposite coefficients. So, the step that I would do first is I would multiply every term on one of our equations by -1. When we multiply every term by a -1, this changes to a negative, this changes to a positive, and this changes to a positive. Watch this again if you need to. Rewind this a couple times. Right? When I multiply every term by -1, I have positive, positive, this is now negative. Why do I like that? Because now I can combine the two equations by addition. 3x and -3x disappear. -4y, positive 6y makes 2y. -11 and 21 makes 10. We can divide by 2, and we get y equals 5 for that value. I'm going to pause this now and let you guys go ahead and solve for x. All right, you should have plugged it back into either equation. I'm just going to get rid of all this. I'm just going to plug it into the top equation. We know that y was 5. Okay, so I've got 3x minus 4 times 5 equals -11. 3x minus 20 is -11. Add 20. 3x equals 9. X equals 3. And we have the coordinate 3, 5. All right? Let's try another one. In this problem, none of our coefficients are equal or opposite. Well, I mean, they might, yeah, they're not equal and opposite. Wait, I have a 2, I have a -4. I have a 3 and a 1. Okay? Now we're going to have to manipulate our equations because we don't have coefficients that match up. But the nice thing is I can multiply equations by any number I wanted to. I could choose 5 and multiply each term by 5, as long as I did it to all 3 terms. Now 5 would be a pointless number for me to use, because it wouldn't help us line anything up. But if I multiply the top equation by 2, this 2 multiplies to that 2 and makes a 4x. We still have to, the nice thing about 4x is now we've got 4x and negative 4x. That's why I chose the number 2, is because it allows one of our variables to have equal but opposite coefficients. I also have to multiply the 2 to this 3y to create 6y. And then I also have to multiply it to this 25 to create 50. Okay? So I've taken this original equation and completely rewritten it. Okay? And now that I've rewritten it, I have equal but opposite terms. So now I can combine it by addition, because the x's will cross off, leaving me with 7y equals negative 15 and 30 makes 35. Sorry, negative 15 and 50 makes 35. Divide that out, y equals 5. I'm going to go back to my original equation. I'll choose the top one this time. I'm plugging 5 in for y, and it needs to equal negative 15. Move the 5 over by subtraction. Negative 4x equals negative 20. X also equals 5. And we've got the coordinate 5, 5. And that's our solution. Okay? This problem. Notice now, none of our terms are equal, and they all have the same sign. So there's several options. I can choose to eliminate the x's, but that would mean I would have to multiply the top by 3 and the bottom by 2. And one of them would have to be a negative, so either negative 3 or negative 2, because I need the signs to be opposite. But that means I have to multiply both equations. If you look at the y value, or sorry, the y variable, I only have to manipulate the top equation, because the bottom one, there's a 3y right there. And I can make 1y become 3y very quickly. So I only have to manipulate the top equation. We like choosing variables to eliminate when you only have to multiply one equation. Okay? When I do that, I do need to multiply by a negative 3 to create an opposite coefficient there, right? In doing so, negative 3 times y becomes negative 3y. But don't forget, you have to do it to all the terms on top. So negative 6x, negative 3y, and negative 1. So these bottom two equations are now the two equations I'm going to use. Okay? So I'm going to get rid of this. And again, you can watch this as many times as you need to make sure that you're mastering this content and learning it. Now they are equal and opposite coefficients of y. They'll cross off. This becomes negative 3x. This becomes, this should have been a negative 3. My fault, I multiplied that wrong. Go back and watch it, you'll see that I should have made that a negative 3. Negative 3x equals negative 3. Divide it out, x equals 1. Okay? Alright, so now that I know x equals 1, I can go back to this top equation. I can plug in 1 for x and solve. 3 plus 3y equals 0. Subtract this 3 to the other side. 3y equals negative 3. Y equals negative 1. And now we have the ordered pair coordinate 1, negative 1, which is our final answer. Okay? All right, looking at this problem now. Again, you can pause this, slow it down as much as you want to. Looking at this problem, x's are not lined up. X's are not equal and opposite coefficients. Y's are not equal and opposite coefficients. And there's no way for me to take 2 and multiply it to be 5, or the other way, there's no way for 2 to become 3. So I am going to have to, in this case, multiply both equations by something. Okay? So I'm actually going to group this, make it just a little smaller, so I can give myself some room for over there. Okay, so I am going to look to eliminate the y value. The reason is because one term is already negative and one is positive. So this makes it a much easier problem knowing that one term is negative, one is positive. Okay? And basically, if I want to get this 3 and this negative 2 to have equal but opposite coefficients, I think of what is the least common multiple between them, and that's 6. So basically, I want to take this 3 and make it a 6, so I multiply it by 2. I want to take this negative 2 and make it a negative 6, so I multiply it by 3. Okay? And watch what happens. So I multiply basically, because if you notice 2 times 3, 3 times negative 2, we should end up with y coefficients that are equal and opposite. All right, please watch this right quick. 2 times 2x is now 4x. 2 times 3y is plus 6y. 2 times 16 is 32. Going to our other equation, when we distribute this 3 times this 5x, we've got 15x. We've got negative 6y. That's exactly what we wanted because now we've got equal and opposite coefficients, and we've got equals 6. Now you should notice that I can combine by addition because those equal and opposite coefficients should be eliminated. 4x and 15x now makes 19x. 32 and 6 makes 38. X equals 2 when I divide that out. Okay? And now we can go to any of our equations that we created. I'm going to go to this equation, and I'm going to plug 2 in for x. So I've got 4 times 2 plus 6y equals 32. 4 times 2 is 8, so I'm just going to subtract 8 to this side. 6y equals 24. Divide by 6, y equals 4. And now we have our solution, 2 comma 4. Okay? Hopefully this is helping us. I would definitely suggest us going moderately slowly through this. I'm going to have you press pause now and try to solve this by eliminating the x. Go to eliminate the x. All right, you probably have unpaused it now because you've solved it. I'm going to multiply the top equation by 3. That becomes 6x minus 12y equals 6. I'm going to multiply the bottom equation by 2. That becomes negative 6x minus 6y equals negative 6. Now I can combine by addition because the x's get eliminated. Negative 18y equals 0, which means y must equal 0. I can plug that into this equation. I've got 6x minus 12 times 0 equals 6. 6x equals 6, x equals 1. Now I've got the coordinate 1 comma 0. That is my solution. All right? Which brings me to one of my last examples. This one is incredibly important for y'all to understand. All right, when you look at this problem, we can multiply the bottom equation by 3. What we will end up with is negative 3x minus 6y equals 21. See what I did there? 3 times negative x is negative 3x, 3 times negative 2 is negative 6y, 3 times 7 is 21. That's the only way that we could have taken the bottom equation and lined up equal and opposite coefficients. The only problem now is that both sets of coefficients are equal and opposite. Well, what's going to happen if both sets are equal and opposite? They're both going to cancel out. Meaning we've got 0x, 0y. Meaning we've got 0 on the left side. And on the right side, we've got 29. Well, this is a crazy statement. When does 0 equal 29? Never. 0 never equals 29. They're not equal. In fact, it's not true. We have produced a always false statement. And if we have an always false statement, that means that there is no solution. Well, what does it mean when we try to solve a system of linear equations and we get no solution? Well, that means we had, from the beginning, parallel lines. Basically, it means that we had two lines that ran parallel to each other and never intersect. That's kind of what's going on here, right? Similarly, if you ever whittled down two equations and you get some true statement like 3 equals 3, where it's always true, then we know that we have an infinite number of solutions. And that is the situation where the two lines are directly on top of each other, okay? So kind of keep thinking this stuff through. I hope that that's helped.